Okay, basically now in this slide we are going to understand what is the meaning of electrode potential. So when we look at this diagram, this is a electrode potential at where basically it is only involved half of the galvanic cell at where there is a metal electrode immersed into an aqueous solution, and there must be contains the metal ions. So what is the meaning of electrode potential? Basically, its ability in bahasa is called keupayaan to attract the electron towards it. So another terms, maybe we can say that it is the potential difference between the metal and the solution which containing the metal ions. So the equation basically can be represented like this. The solution ion or the metal ions need to gain the electron to form metal. So we want to find the potential difference between the metal ion with the metals. So the potential difference between the metal and the solution cannot be measured directly if we only have half cell like this. Therefore, we need a reference electrode. Okay, so this reference electrode normally is referred to hydrogen electrode, at where the potential is always equal to 0. So another terms to represent this hydrogen electrode, we will know it as standard hydrogen electrode, SHE, at where the apparatus set up, it will be looks like it's another half cell of the galvanic equation. Okay, at where because of the hydrogen is always exists in the gas, so that's why we need a boiling tube. Okay, and then we need to have the platinum electrode, and again we need to have the solution which containing the ion, hydrogen ion, so it's H plus. Let's have a look on the example. Let's say we connect the SHE cathode with the zinc anode. So because of the value of the SHE is always 0 watt, so from here it's showing 0.76. So we know that the electrode potential for zinc is negative 0.76. Okay, later we will use one formula. E naught cell will equal to E naught cathode minus E naught anode. So in this case, the reading at the voltmeter basically is considered as E naught cell because they are combining the two electrode potential, which is half from the zinc and also SHE. So because of SHE, just now we say it is a reference and then always is in 0 volt. So let's say we put 0 at the cathode and then minus the anode, the electrode potential, we need to figure out basically. But because of the E naught cell is 0.76, so that's mean we didn't know the value of the electrode potential for the anode in this case. So when we move this one to the left hand side, the E naught anode to the left hand side. So and then we will use 0 minus 0.76, which is equal to negative 0.76 volt. So at now here, based on this formula, then we will know that the electrode potential for zinc is negative 0.76 volt. Okay, later you may see the word standard electrode potential. So like in the thermal, when we have the term standard, so at the symbol there we will have a naught, which is not equal as electrode potential. So the symbol for electrode potential is only the capital E. So basically, same case with the thermochemistry. If standard electrode potential means that the electrode potential is measured at standard condition, which represent 25 degrees Celsius, 1 atm, and this time because it will focus on the solution, we also need to consider the concentration of the solution is 1 molar. So if the concentration of the solution is not 1 molar, let's say is at 25 degrees Celsius 1 atm, but the concentration is 0.5 molar, then the electrode potential that we measure, we will consider, or we know it as electrode potential, because it is not at standard condition. Okay, so it's at any stated condition except standard condition. Okay, this is the previous diagram that show you at where we know that zinc is the anode and then SHE act as the cathode. At where from here we know that the standard electrode potential for zinc is negative 0.76 volt, while for the SHE is 0 volt. Okay, so we have another case here. Now the E naught cell is showing 0.34. So as just now we say that E naught cell equal to E naught cathode minus E naught anode. So cathode in this case is copper, at where let's say we have no idea what is the value, and then the anode is the SHE, so it's equal to 0. The E naught cells showing in the voltmeter is 0.34 volt. So basically from here we also will not know that E naught cathode is equal to 0.34 volt at where is positive. So again, so in this case we know that from these two examples we know that the standard potential, standard electrode potential for anode, standard electrode potential for anode is always more negative than cathode. Okay, so again we look at here, anode negative 0.76, and then SHE is 0, so anode is more negative. Okay, in another example here, anode is 0, and then the cathode copper is positive 0.34, 0 and positive 0.34, 0 is more negative. Okay, so again, from here, just want to make the conclusion, very simple conclusion, that the value, the electrode potential for SHE is always equal to 0. And then the electrode potential, which is more negative, also always will act as the anode. So basically, after we calculate the half cell, which is means the electrode potential, okay, basically we can say that when we measure the half cell, the value that we get is known as electrode potential. If it is not carried out at standard condition, we can mention that this value is standard electrode potential when it is measured at standard condition. Okay, so condition. Okay, and then another term that we want to remark over here is electrode potential, also can known as reduction potential, because generally we will have a table like this. This is just part of the table showing that the half equation is in reduction form. If you notice, chlorine, the oxidation number is 0 and then reduced to -1. Pb2 plus positive 2 reduced to 0. So they are in the reduction half equation. So that's why besides calling this value as electrode potential, we also can note it as reduction potential. So basically you will write down the table like this, and then you will arrange from positive to the negative value. Then as where the hydrogen SHE is the reference, at where the value is always equal to 0. Since the equation is always, the half reaction is always in the reduction form, so all the species at the reactant side, because they undergo reduction, we will note it as oxidizing agent. While the product side, which is this column with the box, inside the box here, will be the reducing agent. Okay, so the table just now is showing that the standard electrode potential series, or we also can notice the standard reduction potential, at where basically it is only represent half cell of the galvanic cell. So from the terms series here, that means there is a number of the metals or the substance that we're going to measure the electrode potential. So based on the table just now we showed in the previous slide, all the half equation always is right in the reduction form. This is also why the series also we can known as the reduction potential series. So and then we always arrange them from more positive to more negative value. So the left hand side, because it's in the form of the reduction, so the left hand side substance at the left hand side of the half equation always as the oxidizing agent, while at the right hand side will be the reducing agent. At the same time also, when we base on the both half equation, two galvanic cell which involve the SHE, one is as the anode and then another one is at the cathode. So we notice that the more positive electrode potential always will be at the cathode. So this is how I remember here. Positive, we have a T which is plus, and then cathode also have a T. Okay, so which is a plus sign. So I will remember like this, the more positive value always will become the cathode in the cell, in the galvanic cell. Okay, the sign of the anode cell will be changed when the reaction is reversed, just similar like the thermochemical equation. If chlorine gas as the reactants, the electrode potential is plus 1.36 volt, while the other way around, if the chlorine gas as the product, so the electrode potential will become negative 1.36 volt. However, another part here, when you're changing the stoichiometric coefficient, let's highlight here, when you're changing the stoichiometric coefficient, it is different from the thermochemical equation. It will not change the value. Okay, so here one mole of gases, positive 1.36 volt. 0.5 mole of chlorine gases, the electrode potential will still 1.36 volt. Okay, before continue with the tutorial question, let's recall back. In the first video that in the chapter electrochemistry, we say that reduction always happen at the cathode. And then the half cell with the more positive electrode potential will chosen as cathode. So by using this idea, let's answer tutorial question number 6. So by referring to SRP table, SRP stands for Standard Reduction Potential Table, at where you can find at the front of your tutorial book or at the back of the tutorial book, there is a list to show that in the half equation in the reduction form and then with the electrode potential. State which species in each pair has a better oxidizing agent. As we know, oxidizing agent always undergo reduction. Reduction always happens at cathode, and the one with the electrode potential, which is more positive, will be the cathode. So now try to check at the left hand side there, because oxidizing agent is the species undergo reduction, so they will at the left hand side of the half equation. So the electrode potential for bromine is 1.07, while Au3 plus is 1.50. So between these two values, 1.5 is more positive. So Au3 plus is the oxidizing agent in this carbonic cell, while the H plus is with the 0.00, silver ion is 0.80, so 0.80 is more positive. So if you have a silver half cell with the SHE, silver will become the cathode. CD2 plus is negative 0.40, while chromium is negative 0.74 volt. So for this case, CD2 plus is the anode, is the cathode, which undergo reduction and act as oxidizing agent. Then the next one is the oxygen in the acidic medium. So try to look at if oxygen in the acidic medium. So beside from the oxygen in the half equation, you also will see H plus in the half equation. So for this one, the value, the SRP value is positive 1.23. Then try to look for another half equation. There is oxygen and in basic medium, which is OH negative. So at here we can see that the SRP value is positive 0.40. So between these two, oxygen in the acidic medium with the more positive electrode potential, so it will act as cathode, undergo reduction, and will be the oxidizing agent. Let's proceed to tutorial question number 7. Again, also referring to the SRP value with SRP table. So choose which one has a better reducing agent. So as we know, reducing agent always undergo oxidation, and then need to happen at the anode. So the SRP value, which is more negative, will be chosen as anode. So again, also refer to the SRP value. The SRP value, okay, so then you have to make sure because the reducing agent is undergo oxidation. So you have to make sure that all the species sodium, lithium, hydrogen, iodide ion, Fe2 plus, Ag, Br negative, and cobalt 2 plus is at the right hand side of the equation. Right hand side of the equation. Yes. Okay. So when you look at the value, sodium will having the value negative 2.71, while lithium is negative 3.05, at where lithium is more negative. Hydrogen is 0, and then I negative is 0.53, so hydrogen is more negative. Fe2 plus is 0.77, positive 0.77. Ag is positive 0.80. So Fe2 plus will be the better reducing agent. Br negative is positive 1.07 and cobalt 2 plus is 1.82. So Br negative is more electronegative. Okay, now look at tutorial question for the objective question number 2. The value for the E0 cell of 2 electrodes are given. So you will notice that sodium plus to sodium is reduction form. Ce4 plus to Ce3 plus, both of these are in the reduction form. So we can say that this is part of the SRP. So by referring to the ions and atom given, choose the strongest oxidizing agent. So as we know, oxidizing agent will be the species undergo reduction and suppose always act as the cathode, and then the E0 electrode should be more positive. So when we look at here, positive 1.61 is more positive. So then we have to look at undergo reduction. So we have two choices here, Ce4 plus and Ce3 plus. So the species which undergo reduction is Ce4 plus. So that after undergo reduction, it will become Ce3 plus. So from here we know that the answer for the sodium boy and donkey will be out. So next part is the reducing agent. So reducing agent is the species which will undergo oxidation and then happen at the anode with electrode potential which is more negative. So again, so Na plus and the Na is more negative. So then we have to check which one is undergo oxidation. Na plus undergo oxidation or Na undergo oxidation. So if very obvious is Na goes to Na plus, the oxidation number is increased. So that's why Na is the reducing agent. So the answer for this question is A.